So here's how we pick that perfect distance. Remember our sampling distribution. From the central limit theorem, it tells us that we've got a nice normal distribution shape here. And we know that the mean for the sampling distribution is the same as the mean in the population. Now, before we went on break, we started talking about computing the middle 95% or the middle k% for a sampling distribution. And essentially what this meant is that there's a 95% likelihood that the sample mean we will observe is within a certain margin of error from the population mean. Now, equivalently stated, what this means is that once we take a random sample and look at the sample mean, if we create an interval at x bar minus e to x bar plus e, 95% of the times, that randomly generated interval ends up containing the real population mean. Let's take a look at another simulation. Okay, so looking at this visualization, this purple line here is the density curve for our sampling distribution, right? It's our normal distribution. It has its peak, which is represented with this green line here, at the population mean. This is what we're trying to estimate, right? And its standard deviation is our original population standard deviation over square root of n, right? We're applying the central limit theorem here. I've highlighted in blue the middle 95% for that sampling distribution. And what we can see as I click this Get What Sample button is it'll take a random sample from the population, compute the mean, and it'll plot where that mean falls on the x-axis, right? And what you'll notice is as I keep clicking this, for the most part, the observations that I observe, right, the sample means that I'm getting fall in that blue region. And this should be expected, right? This is the 95% middle of that sampling distribution. So 95% of the time, the random sample I collect will fall in the blue region. Now, if I take this margin of error that goes from the green line out to the edge of this middle 95%, if I use that margin of error to create a confidence interval, you can see how often this confidence interval actually overlaps with the real population mean. Right? So long as my sample mean estimate, right, this vertical blue bar, stays inside the middle 95%, this confidence interval that I generate using that same margin of error ends up capturing the population mean. Now, every once in a while, we're going to end up with a sample mean that's outside of that middle 95% for the sampling distribution. And in that case, it turns out that the confidence interval we generate doesn't overlap with the population mean. So this is a mistake. This is why we don't get 100% success rate when we do this confidence interval process. But the main idea is that 95% of the time, I am getting a good confidence interval. Or in other words, those bad confidence intervals are pretty rare. They should be occurring less than 5% of the time. So our odds are pretty good that we can trust the confidence interval we do make from collecting one sample led to a sample mean in the blue region, and hence a confidence interval that contains the actual population mean. So, short story, the way that we want to lengthen from that sample mean to create our confidence interval, it's the same length, it's the same margin of error we would use when finding a middle percentage of the sampling distribution. All right, one more recap. So the question was, how far should we move from x bar to create our confidence interval? And what I'm telling you is the same margin of error that we used to compute that middle 95% of the sampling distribution should be used to move away from our x bar estimate to create our confidence interval. So the same distance from the center of our sampling distribution out to the edge is going to give us the right margin of error. The other nice part is that the middle percentage we choose is actually going to give us our success rate, or what we'll eventually call our confidence level. So here's our confidence interval process. We're going to start out determining the confidence level, which I'm using k because this is what we're familiar with as being the middle k% of a distribution. Same idea. We're going to find what kind of percentage is missing and divide this area into two tails. So essentially we have the following picture, which again should be familiar to you. We've got the middle k%. Alpha is the missing percentage, which we divide in half and put into each tail. Now, we had this in the previous work. We tried to figure out what this margin of error was to kind of get to that right edge of our middle k%. The general formula is we have that critical value, z alpha over 2, times the standard deviation of the distribution. But since this is the distribution for the sampling mean, we apply our central limit theorem and get a formula of sigma over square root of n. So this is going to be the length that we're going to move away from our sample mean estimate in order to create our confidence interval. So in terms of our steps, once we know our confidence level, we'll find alpha and we'll divide that alpha in 2. Remember, z alpha over 2 is that special critical value. So this is the same thing that we did when we were finding our middle percents. We find the special z-score, the norm.s.inverse command will give this to us. And then the formula for our margin of error in this case is going to be our critical value times the standard deviation in the population over the square root of the sample size that we'll use. Finally, to create our confidence interval estimate, we'll take our actual sample mean, which we got from our data, and we'll just subtract this margin of error to get the lower bound, and we'll add that margin of error to get the upper bound. And the benefit of doing this is that this interval, which is randomly determined, right? Since our sample mean is randomly determined, where this thing is centered is going to be randomly determined. This random interval is going to actually overlap with our population mean k% of the time, or in other words, our success rate is going to be the same thing as this confidence level that we set at the beginning. Okay, so let's consider an applied example and walk through this confidence interval process. Here's our setup. Suppose we create a simple random sample of 50 people from Massachusetts, and we record their household income. For the 50 people that we put in our sample, the mean income is $63,500. We're also going to assume that the standard deviation of incomes across all of Massachusetts is 14,000. With a confidence level of 96%, what we want to do is create a confidence interval for the population mean income for all of Massachusetts. Let's visualize this quickly. I'm going to put a little whiteboard sketch together to show you the roles of the central limit theorem, and then we're going to walk through the steps of actually computing our confidence interval. So let's think about the incomes for residents in Massachusetts as being a random variable. So let's let x be the income for residents of Massachusetts. Now, if we were to think of this as a data set, we wouldn't necessarily know what the shape of its histogram might be like. On the probability side, that means we don't really know what the shape of that density curve ends up looking like. So I'm just going to draw a little sketch. We can't make any assumptions about this shape, right? So maybe it has a couple of spikes, etc. But certainly this density curve, or if you think of it as a histogram, will have a balance point. In other words, it'll have a nice population mean. And this is exactly what we're trying to estimate. Okay? Now in our case, keep in mind that we're looking at samples of size 50. Now this is certainly greater than 30, which means the central limit theorem will hold. So if we consider the distribution of sample means, so x bar we're going to let be our sample mean for a group of 50. Because of the central limit theorem, we know that x bar is going to have a nice normal distribution. Moreover, its peak is going to be sitting exactly at the mean in the population, at the population level. Now we get to make one other nice assumption in our problem. And to ferret out what information we're going to use next, it's a good idea to kind of work sentence by sentence. So I can do this by actually just breaking up the individual sentences. Our first sentence, suppose we create a simple random sample of 50 people from Massachusetts and record their household income. This is telling me essentially my sample size. The second sentence, for those 50, the mean income is $63,500. This is giving me some information about my sample. It's the third sentence that we're going to use next. We assume the standard deviation of incomes over all of Massachusetts is 14,000. This is a statement not about a sample mean, it's a statement about our actual population, right? This is a parameter. What this is telling us is that the amount of variation that we would see in the population, right, our sigma value, is equal to 14,000. That's an assumption we're making for this particular model. Now, this is particularly helpful because the amount of variation that we end up seeing in X bar through the central limit theorem ends up being computed from that population level standard deviation. In our case, we know that we'll take our original population standard deviation of 14,000 and divide it by the square root of our sample size, which is the square root of 50. Okay? So now we know that our sample means that we're going to collect will be relatively close to our population mean. And in fact, we can even quantify how much variation away from that population mean we'll have because of the central limit theorem estimate for what the standard deviation in that sampling distribution will be. All right. So the idea behind the confidence level, or sorry, the confidence interval, is to say, take a look at this sampling distribution and think about the middle, let's say 96%. So I'm using the confidence level provided in the problem, and I'm thinking about that as the middle percentage for my sampling distribution. Now what this means is that when I go out and grab a random group of 50 people from Massachusetts and compute their mean income, 96% of the time, it should fall in this little blue region. So what this means is that my sample of 50 people, which led to a sample mean income of 63,500, pretty much has a 96% chance of falling somewhere in here. Now, I don't know where exactly it's going to be. Let's say it's over here, 63,500. But I do know that 96% of the time you get a sample that's in this blue region. And what that forces is it essentially gives us a confidence level that the sample we did collect is in that little blue region. Now our next step is to widen our estimate rather than just using X bar as our estimate. What we're going to do is kind of create a confidence interval. We're going to look at a little interval of scores centered at the 63,500 plus a little bit of a margin of error. And we'll be 96% confident that our random interval that we just generated actually does capture that population mean. Or in other words, this interval overlaps with the peak of our sampling distribution. And what we saw in the previous case was that the margin of error that we should use when generating our confidence interval is the same thing as our critical value, z alpha over 2, which we computed when we were doing middle percents, times the updated standard deviation given to us by our central limit theorem. In other words, it's the standard deviation of our sampling distribution. So once we figure out what our margin of error is, and once we know where the center of our interval is, all we have to do is compute our confidence interval by taking x bar minus the margin of error and x bar plus the margin of error, and that's going to describe that yellow region that we highlighted above.